We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
It is, as we know that the rising main or pumping main, or which we can say transmission main, is the pipe through which the water is pumped to the treatment plant. And the diameter of rising main needs to be optimized to reduce total annual expenses and thus achieve economy. Right? We cannot directly assume any diameter and we can provide any diameter of the pipe, but we have to optimize this. How to optimize it, we'll see later on. If the size is too small, the cost of pipe is less, but frictional losses are high and pumping cost will be more, right? So this is one parameter to optimize the pipe, right? If the size of the diameter is small, then the cost of pipe will be less, but frictional losses will be high. And if the frictional losses are is high, then the total head required will be more, and if the total head required is more, then the pumping cost will be more. And if the size is too large, then the cost of pipe will be more, but frictional losses are less. And if the frictional losses are less, then pumping cost will be less. So we have to see between these two parameters, and using these two parameters, we have to optimize the diameter so that um, the annual expenses can be reduced and we can achieve economy. The pipe diameter and material is selected such that overall cost of the project should be minimized from both operation maintenance and construction point of view. And the diameter which provides such optimum condition is known as economic diameter of pipe, and we'll see one example how to calculate economic diameter of the pipe also. But there is one formula given by Lee which states D is equal to 0.97 to 1.22 under root Q. So using this we can calculate economical diameter of the pipe. D is equal to diameter and Q is discharge in meter cube per second. So we'll see one example of gravity main, how to design gravity main and how to design one rising main. We'll see one example first for gravity main. So here it is given water is to be supplied to a town of population 1.5 lakh. If the waterworks is situated at a lower elevation of 50 meters than the water level in the source, determine the size of gravity main to convey the water from source to the waterworks. If the length of gravity main is 25 km and per capita water demand of town is 150 liters per capita per day, and take F 0.075. So in this example, population is given, then elevation difference is given. Now here the source is situated at higher elevation, right, and the water treatment plant is situated at the lower elevation. So that's why gravity flow is possible. Total length of the gravity main is 25 km and water demand is 150 liters per capita per day. So total quantity of water required by the town is total population 1.5 lakh multiplied by 150 liters per capita per day. So this will be equal to 22,500 meter cube per day, right? And if we consider that water is supplied for 12 hours, then Q for 12 hours will be 22,500 divided by 12, so that will be equal to 0.52 meter cube per second, right? And Q is equal to, we know that Q is equal to A into V, so this will be equal to pi by 4 d square into V is equal to 0.52. So from this we can obtain V is equal to 0.66 divided by d square. The V is in the form of d. Now we know that for head loss, Darcy-Weisbach formula, it states that HL is equal to FLV square upon 2GD. F is given, which is 0.075. L length is 25. It is converted in meter. 25 multiplied by 1000 divided by 2 into 9.81 into D, right? G is 9.81 into D, and B is 0.66 divided by D square, right? And all square. Now since all available head is lost in overcoming the friction, right? Since this is the gravity main, so that means the 50-meter head which is available at the source is lost in overcoming the friction, right? So basically, if we say this is the source, this is the source, then and this is treatment plant, right? Here WTP is located, and here this is the source. So here 50-meter head is available, right? So this 50-meter head available head is lost in overcoming the friction, right? In friction. So head loss we can consider as 50, or we can consider less also, right? 50. So 50 HL is equal to 0.075 multiplied by 25 into 1000 divided by 2 into 9.81 into D into D square. So using this equation, we will get D is equal to 0.963 meter. So say 100 centimeters. So 100 centimeter diameter pipe is required to supply this much quantity of water. Then see one example of design of rising main. So it is given that water is to be supplied to a town of 2 lakh population from a source 1.5 kilometer away. Per capita demand of the town is 180 liters per capita per day. If the town is situated at higher level than the source, and the difference in elevation between the lowest water in the source to the point of inlet at the waterworks is 27 meter. Determine the size of rising main and HP of the pump. Take CH110 and pump works for 18 hours. So let's first understand what is given to us. First, population is given, which is 2 lakh. Then from source to our city situated at 1.5 kilometer away. So the length of transmission main or rising main is 1.5 kilometer. Per capita demand is 180. And next important thing is given is the difference in elevation between lowest water in the source to the point of inlet at the waterworks is 27 meter. That means if we consider this is the reservoir, here one intake is situated, and this is the ground elevation, this is the ground profile, and here our city is situated, so this is the inlet. So from here, this is the lowest water level, say this is the lowest water level, right, from where we are withdrawing the water, right? So between this lowest water level and the point at this inlet, the elevation difference is 27 meter, right? So this 27-meter head is called static head, right? Difference between this lowest water level and the point of inlet, right? Ground elevations or the elevations at the inlet is called static head, right? And which is 27-meter. But suppose if the ground profile is like this, right? Then this is the highest elevation along the route. So instead of considering, if this kind of situation is there, then instead of considering elevation as this point, we should consider highest elevation along the route, that is this point, right? Because elevation at this point is lower compared to this point, right? So during this kind of situations or during this kind of terrain, we should consider highest elevations along the route. So in our case, the highest elevation according to this sum, it is here. But if the highest elevation is suppose here, then we have to consider highest elevation along the route. So in this example, quantity of water required by the town is 2 lakh population multiplied by 180, right? So Q is equal to 36 multiplied by 10 raised to 3 meter cube per day. Now pumps work for 18 hours per day. So Q will be 36 multiplied by 10 raised to 3 divided by 18. So that is 0.555 meter cube per second. So now assuming velocity of flow through pressure pipe is 1.25 meter per second, you can assume different velocity also. So for this velocity, cross sectional area required A is equal to Q by P, right? So Q is 0.555, V is 1.25, right? So from this equation, D is equal to 0.75 or say 80 centimeter. So if we have rounded this figure 80 centimeters, so actual area provided is 0.5024 meters square, and actual velocity will be V is equal to Q by A, right? So Q is 0.555 divided by 0.5024, so which is 1.1 meter per second. This is velocity. Now loss of head by Hazen-Williams formula, this V is equal to 0.85 CH into R is to 0.63 into S is to 0.54. We know this is Hazen-Williams formula. So R is D by 4, right? For circular pipe or circular conduit, R will be always equal to D by 4. So D is 0.8 divided by 4. So this will R will be equal to 0.2, right? So if we put this figure in this equation, V is equal to 1.1 CH. This coefficient, Hazen-Williams coefficient, is given as 110. This depends on the roughness or smoothness of the pipe. R is 0.2 and this is S. So if we calculate or simplify this equation, then S will be is equal to 0.001737. Now this indicates head loss per meter length, right? So head loss per meter length is 0.001737, right? Meter per meter head loss is there, right? So this is HL by L, head loss per meter length. So total head loss will be equal to 0.001737 multiplied by total length of the pipe, right? So this is per meter length and our total length of the pipe is 1500 meter. So the total head loss will be equal to 2.605 meter. So this means that in 1500 meter length there will be 2.605 meter head loss. So the total the height difference between low water level to waterworks, which is given as 27 meter. So this is the measure, or which we can say the static height, and this is head loss in rising main, which is 2.6 meter. So total height required will be equal to 27 meter plus 2.6 meter. So this is 29.6 meter, right? Now what is this total height required? This is the actual height required at the source, right? If we pump the water, or if we provide the pump with 29.6 meter head, then the water will reach up to the inlet point. Now here we have not considered minor losses. We have considered only the static head plus the head loss along the pipe. We have not considered the minor losses. So you can consider minor losses as 10% of the total head also, right? So HP is equal to, this is the formula of horsepower, QWH upon 75 eta. Eta is the efficiency of pump, H is total head, W is density of water, and Q is equal to discharge required. So Q is 0.555 multiplied by density of water 1000 multiplied by total head, which is 29.6 meter, and divided by 75 into eta is 0.7, right? So efficiency we are considering here as 70%, right? You can consider more efficiency also. Here efficiency is not given, but we have considered 70% efficiency. So from here the HP required is 312.9 HP, right? So using this we can select the pump also, but this is uh, for the academic purpose. But if we are designing the pipeline or rising main, then we have to work as per, or we have to design as per the CPHEO guidelines, right? So that is the techno-economical size for the pumping main. So I will show you one example how to calculate economic size of pumping main as per CPHEO manual, right? So the basic philosophy behind this techno-economical analysis is, if we increase the diameter, then frictional losses will be less and pumping cost will be less, but the pipe cost will be more. And if we decrease the diameter, pipe cost will be less, but frictional losses will be more. So the pumping cost will be higher, right? So we have to find out one point between these two parameters at which uh, the overall cost of the capitalized cost is minimum, right? So here it is given that required discharge is 1.3 mld and total length of the pumping main is 2.4 kilometer. I'm not going to explain each and everything in this techno-economical analysis. You can go through CPHEO manual, and very good explanation is given in manual water supply and treatment manual, right? So water requirement 0.015 meter cube per second. Intermediate and ultimates are same, and many times intermediate or intermediate and ultimate demand may different, right? So length of pumping main is 2.4 kilometer. Minimum water level at source is 93, and maximum ground level in pipe root is 100. And so the residual head, right, this is the head required at the end, right, so that the water can flow. So this is generally we are taking 3 meter. Static head, this is the difference between this maximum GL and minimum water level. So this is 10.43. Design period we are considering 15 years for all mechanical parts, like pumps we are considering 15 years, and for civil work we are considering 30 years as the design period. Combined efficiency of pump set we have considered 70%. Cost of pumping unit 27,000 rupees per kilowatt. Interest rate 10%. Life of electric motor and pump 15 years, right? And energy charges 5.8 rupees per unit. C value for DI pipe we have considers 140 and standby kilowatt 50%, or we can say we are providing 50% standby because we are considering two pumps only here. So that's why we have considered 50% standby, but actually we can provide 25% standby also. So hours of pumping we are considering 6 hours. So design discharge for this 6-hour pumpings will be 216.67 meter cube per hour. Now here the kilowatt requires, what are the kilowatt requires, it is considered in terms of, or it is calculated in terms of head, right? So 0.84 into H1. So as the head is changed, then the kilowatt will change, right? So this is the equation for pump capitalized cost. This is for energy charges capitalized, and this is Hazen-Williams formula. This we have already seen. So if we consider different diameter of pipe and frictional losses, as we have considered, we have calculated in previous example, like frictional losses will be different, right? So as we can see, frictional losses a meter per 1000 meter is different, or for lesser diameter of pipe, more friction losses are there, and higher diameter of pipe, friction losses are less. And you can see the velocity also. For 100 size, velocity is 7.66, and for 350 it is 0.62, right? So velocity will also decrease if we increase the pipe diameter, right? So this is the total frictional losses. Other minor losses we have considered 10%, so this is total losses, right? So for 100 pipe to 350 pipe, the total losses for 350 pipe is 13 meter. Now this is what are the kilowatt required and cost of pump set, because if the head loss increase, then the cost of pump will increase because the kilowatt requirement will be more, right? So for 100 pipe, total kilowatt required are 1500, and for 350 size pipe, the total kilowatt required are only 60. So you can see the variation in cost of pump also, right? For lesser diameter of pipe, cost of pump is more because the total kilowatt is higher. Why the total kilowatt is higher? Because the total head requirement is more. Why the total head is more? Because frictional losses are more, because we are providing lesser diameter of pipe. And for pipe cost, we are considering GWSS BSR 1920. So for different diameter of pipe, we are considering DIK9 pipe. We have added GST also. So this is the total pipe cost, labor cost for lowering and laying, and this is total pipe cost for all size of pipe. Right? And this statement show comparative statement of overall cost structure of pumping main for different pipe size. So for 100 pipe size to 350 pipe size, what is the total cost of pump set? Then these are the energy charges, and this is the grand total or the capitalized cost. So for 100 diameter pipe to 350 diameter pipe, the price or the cost or grand total of capitalized cost is changing. For 100 it is higher, then it is decreasing, then it is decreasing, and for 250 it is less, and then it is increasing, right? Because the diameter, as the diameter increase, the overall cost is increasing here. So this 250 diameter pipe is the optimum, or we can say it is the economic pipe, because for 250 diameter pipe, grand total capitalized cost is less. So for economic diameter is 250 For this 250 dia pipe, velocity is 1.23 meter per second. Head loss per kilometer is 5.32, and total head required For 250 mm dia pipe is 24.48 meter. Right. So using this, we can design a pipeline or rising main, or we can consider techno-economical analysis of rising main. So now these are some pumps requirement, right? A pump is a device which converts mechanical energy into hydraulic energy, and various purpose pumps are required. First, to lift the raw water from wells to treatment plant, or from source to treatment plant, for filling ESR or elevated service reservoir to deliver treated water to consumer, and to supply the pressure water for fire hydrant, and to boost up the pressure in water mains, to fill elevated ESR or backwash filter, many purpose. So thank you. I hope you have understand all about the conveyance and collections and conveyance of water. Thank you.